Welcome to the class. In last lecture we had seen that the velocity triangles, how do they exist for the centrifugal compressor. So we are in the phase of understanding centrifugal compressor. In that case we had seen that centrifugal compressor has possibility of two types of inlet velocity triangles. In one case we can have inlet velocity which is absolute velocity, which is C1, which can be axial velocity, and then that velocity is the inlet velocity at the inducer, and then but the flow actually enters tangentially to the blades, and then this is our u1 rotational speed. So in this case we had seen that absolute velocity is perpendicular to the u. This is without inlet guide vanes. This is without inlet guide vanes, which we had seen. Without inlet guide vanes. But with inlet guide vanes, we have, instead of this, we have absolute velocity which is coming like this due to the inlet guide vanes. We initially had this u1, so we have this as v1, and then this is c1. So this is alpha 1, this is beta 1. Here this is beta 1 and this is alpha 1. So this is with inlet guide vanes. This is what we had seen in last class. Then what we had seen, that apart from these two possibilities of inlet velocity triangles, we had three possibilities of outlet velocity triangles, and then very first simple was the case of radial vanes. If we have radial vanes, then what we would have is the velocity which is going out is v2, but then we had this as u2, so this will turn out to be c2, and then this is alpha 2, and then this is beta 2. Just for reminder, what we had we are considering is the centrifugal compressor. So for centrifugal compressor, we know that for any compressor we have first rotor and then we have stator. So 1 to 2 to 3, this is what our arrangement is. So 1 to 2, what we are talking about, this is 1 and this is 2. We are talking at the rotor inlet as 1 and we are talking about rotor outlet as 2. So this is for radial vanes, or we also know it as beta 2 is equal to 90 degree. But in other case, if we have the vanes to be non-radial, then we had seen that in a case where they are backward faced, then in that case first we had this as u2. We have to remember that u2 is parallel to the arc of the circle whatever we are drawing, and then this is v2, and then this turns out to be the c2. v2 velocity is tangential to the blades, u2 velocity is tangential to the arc, since u2 is the tangential velocity, and then this turns out to be alpha 2, this turns out to be the beta 2, or rather this turns out to be the beta 2. Sorry. Okay. So after having radial blades, we had also seen that there is a chance that there will be blades which are backward facing blades. So in case of backward facing blades, we have a different velocity triangle. So first we have u2, and then we have v2, and then we have c2. So this is the possible velocity triangle for backward facing vanes. So this is beta 2 and this is alpha 2. Here we had seen that this is backward facing vanes, and this is beta 2 which is less than 90 degree. In this case basically v2 is equal to cr2, here this is CR2, and then this is CW2. But now we will draw for the as what we have drawn earlier for forward facing vanes. We have this, we have this as U2, and we have this as V2, and so it turns out to be this as C2. So where we get beta 2 is more than 90, so this is forward vanes, where beta 2 is greater than 90 degrees. So we had seen that there are three options for the outlet velocity triangle and there are two options for the inlet velocity triangle. Having said this, we should now find out what are the outcomes of this velocity triangles. First is, we should know what is W for a stage, that is work input for a stage, and that work input for a stage we know that m dot into U2 CW2 minus U1 CW1, but we will consider it to be specific work input. So for specific work input we will not have m dot, so we will have U2 CW2 minus U1 CW1. Now when we consider the inlet velocity to be coming axially, then we have a chance that we might not have in general we might not have inlet 1 velocity. CW1 might be 0 in a simplified case, so we can neglect this inlet CW1 if it is 0. So if there is no inlet swirl, then CW1 is equal to 0, and then in that case Ws becomes U2 CW2. Assumption is we have CW1 is equal to 0, which is no inlet swirl. No inlet swirl. So in the case of no inlet swirl, we will have swirl velocity or whirling velocity at the inlet is 0. But here we would have some outlet swirl velocity, U2 CW2. Practically speaking, if we go back and if we see the radial case, then in this case U2 is actually equal to CW2 in radial case. Okay, so having known as U2 is equal to CW2, we can write W stage for the centrifugal compressor is equal to U2 square. This is for ideal case. Ideal case where CW2 is equal to U2, but it is not valid in general since CW2 is not equal to U2. There is a reason for that, and the reason is called as slip factor. There is a term called as slip factor, and this has to do with inertia of the flow. The flow has certain inertia, and due to that inertia it is not going to follow faithfully with the blades. So the blade has velocity U2 at the outlet of the vane, but the flow will have velocity CW2 which is not equal to U2, and then associated difference or associated ratio between the two velocities is called as slip factor, which is accounting the inertia. So inertia slip factor, which is sigma, and this sigma is equal to CW2 upon U2, and in ideal case sigma is equal to 1. However, there is a correlation which said that sigma is equal to 0.63 pi divided by n for non-ideal case or real case where n is equal to number of vanes. We can see from here that as number of vanes are increased, we will get higher value of sigma. Okay, so the inertia effect will be reduced, and this should be pointed out here that this effect of inertia will leads to sigma, which is slip factor, but there is no role of the frictional loss here. Sigma is due to inertia. So we would have Ws, which is stage work, is Cu2 Cw2 is equal to sigma U2 square. This is the stage work. But there is one more problem which is due to friction, and then that is called as psi, which is called as power input factor. So this is one, and then there is other which is called as power input factor, and that is psi, and psi is defined as actual work upon ideal work. So psi is equal to actual W stage actual divided by W stage ideal, and then this psi is mainly due to the frictional loss or friction between the vanes and the casing, and this psi has a range which says that psi is going to vary between 1.035 to 1.04. This psi accounts for the frictional loss. So in general, W stage actual what we are having is equal to psi into sigma into U2 square. So this is the formula for work input for a stage for a centrifugal compressor, where U2 will be the velocity at the tip of the impeller, and sigma is the slip factor, and psi is the power input factor. So having said this, now we have to draw the TS diagram for the centrifugal compressor. Again we will remember that we have in the centrifugal compressor we first have rotor and then we have stator. So if we go back and then see, the diagram what we had seen earlier, which is the configuration of the centrifugal compressor, where we can see that this is the I inlet of the centrifugal compressor, and then till this point from here to here we have the inlet accelerating nozzle, from here to here we have inlet guide vane. So these parts were there, however we did not consider them for our velocity triangle analysis, and we consider them for the rotor outlet. We drew the velocity triangle at the section 2. We had drawn the inlet velocity triangle with and without inlet guide vane. So we see that this is I, which is inlet, this is 1 which is at the outlet of the inlet guide vane, and this is 2 which is at the outlet of the impeller, and then this is 3 which is at the outlet of the diffuser. So we will try to draw the velocity triangle, the TS diagram for the centrifugal compressor with these points in mind, where first flow is going from I to 1, 1 to 2 and 2 to 3. So let us continue that and then see. So we have flow which is I to 1, then 1 to 2 and then 2 to 3. Here the flow is between accelerating nozzle, and inlet guide vanes. It is in the impeller and it is in the diffuser. So I to 1, 1 to 2 and 2 to 3. So this is our flow passage. So for that all sake, let us try to draw the TS diagram. So here we have y-axis as T, which is temperature, and x-axis which is S as entropy. Before drawing the TS diagram, we will try to understand one point here, which is called as stagnation quantities, and here that is why this temperature onwards would be represented as not as T but T naught in some cases. What is the stagnation condition? Now we have written the steady flow energy equation as H plus V square by 2 or U square by 2 plus Q is equal to 1 between two stations 1 and 2. We stated that it is H2 plus U2 square by 2 plus W. So there is some work and heat interaction between two stations 1 and 2 if flow is going between two stations. This is a general streamline, and then here we see that if there is no heat interaction, flow is adiabatic. If there is no work interaction, and in this case if we feel that we can isentropically stop the flow at station 1, then what would happen? The velocity of the flow will become 0, and then that velocity which is decreased to 0 would help to rise the enthalpy. So for station 1, if we isentropically stop the flow in an imaginary manner, then we will have H1 plus U1 square by 2 is equal to H01. So this is the stagnation enthalpy for the station 1. So H is called as static enthalpy. We have in the thermodynamics now there are two types of terms which is called as static and stagnation. So in the thermodynamics we just know what is the static temperature, static enthalpy, static pressure. But when we try to account it with gas dynamics, then we have to account the kinetic energy associated with that static temperature, and then if we add the enthalpy and the kinetic energy, then the resulting term would be called as stagnation enthalpy. So accordingly we get a relation which is for the relation between T01 and T, and then the isentropic relation, famous relation for T01 upon T1 is equal to 1 plus gamma minus 1 by 2 m square. So this is the relation between the total temperature and static temperature. This relation can be proved from this expression where we are taking H is equal to Cp into T, where Cp is assumed to be constant, gas is assumed to be calorically perfect, and then accordingly if we derive, then we will get a relation which is 1 plus gamma minus 1 by 2 m square. So here we are having static temperature, here we are having total temperature. Whenever we were interacting for the Brayton cycle in earlier chapters, we were considering TS diagram, and for the TS diagram we were considering only static temperature. So for us compressor work was Cp into T2 minus T1, our turbine work was Cp into T3 minus T4. This was a simplified analysis where we had also stated in that time that in both the cases we are considering gas to be calorically perfect, plus we are considering flow to be adiabatic, plus we are considering that the kinetic energy is negligible in terms of the enthalpy. Since kinetic energy is negligible in terms of enthalpy, we had neglected the temperature to be considered as total temperature, and instead of that we had considered the static temperature. But now we have to consider the energy which is complete energy, and where we have to consider the kinetic energy as well. So if we consider kinetic energy, then compressor work will be treated as Cp into T02 minus T01, and turbine work will be treated as T03 minus T04. The difference between those two formulas is just that we are considering the kinetic energy. So when we replace the static temperature by total temperature, we have started accounting the kinetic energy. Similarly, when we consider the pressure rise or pressure ratio, we had considered P2 by P1, which is the pressure rise in a compressor, but here while dealing with the components, since we have to find out their efficiencies, we will try to deal with the total condition instead of the static condition. So our pressure ratio Rp will also be P02 upon P01. Okay. So having said this, as preliminary information for the stagnation conditions, we will use this for the analysis of the centrifugal compressor. This part, whatever we have dealt with, is part of the course which is gas dynamics, where it is elaborately treated that what do we mean by static condition and what do we mean by stagnation condition. Here we would need these concepts for understanding the flow through the centrifugal compressor or axial compressor or this turbine. So for that we just got the introduction of this point, which is called as stagnation point or static temperature or stagnation conditions. Stagnation conditions are also called as total conditions. So we have two kinds of names to this. We either will call H naught as the stagnation enthalpy, or we will call it as H naught as total enthalpy. Okay. So for that all sake, we were here at I. From I to 1 we would go in the nozzle, but in that case flow is accelerating. Since flow is accelerating, its temperature will decrease, but then there would be losses, so entropy would also increase. So we will come from I to 1 in this phase. Okay. And from 1 to 2 the flow is going through the impeller. So while going through the impeller, we are having the temperature rise, some part of the temperature rise, some part of the enthalpy rise would be happening into the impeller, and then we had 2 to 3 as the diffuser. So we are having nozzle plus inlet guide vane, we are having impeller, we are having diffuser. Okay. So this is the velocity diagram, this is the TS diagram for our centrifugal compressor, but this is not complete. Now if we consider the flow to be isentropically stopped, then what we can get is this as T01. So we would have T01 as the total temperature over here, and then this can further, we can further find out the total temperature, but this height is the kinetic energy corresponding to it. So it is half Cp into C1 square. So we would have stopped this kinetic energy, that's why we have got naught. So this is P01 and then this is P2. Now we will stop the flow at 2 to go to the isentropic state, and then we stagnation state. As we have seen that we are considering that by imaginary process, which is an isentropic process, we are stopping the flow to go to the stagnation conditions. So for that all sake we will reach here at P02, and then corresponding temperature would be T02. However, in this case we will reach here, and this is T02, and then this is half Cp into C2 square. Similarly, if we stop isentropically at 0.3, then also we will get same total temperature, which is T02 is equal to T03. Since there is no work interaction between 0.2 and 3, flow is going through the diffuser, but there is loss in total pressure due to friction. In this direction total pressure increases, so P02 is greater than P03. There is loss in total pressure. Since there is loss in total pressure, we are having friction as a reason for that, and then this is, since flow is not completely stopped, 1/2 Cp C3 square, which is the velocity at the outlet of the diffuser. So in all, what we would have is we were here at naught and we reached here at naught. So this is the actual shaft work, what stage work, what is supplied to the compressor actual. But ideally, if we would have to go to this P03, then we would have to supply this work. So this would have been the ideal stage work. So this is the TS diagram for the centrifugal compressor. So having said this, now we will proceed. We need these total temperatures evaluations in the examples to be solved, so only we have tried to represent them in terms of total temperature. Now our objective is to find out the actual temperature rise in the compressor. So we know that stage work, this specific stage work, whatever we have supplied to the compressor is Cp into T03 minus T01, which is Cp into delta T0 stage in actual, and then that is equal to psi sigma U2 square. We have to keep it in mind, this psi sigma U2 square is a specific number corresponding to radial vanes, and we are considering psi, which is a factor corresponding to friction. Then we are considering sigma, which is again a factor corresponding to inertia. So considering these two factors, we have found out psi sigma U2 square for the stage work, which is actual stage work. So we got delta T0 in a stage is equal to psi sigma U2 square upon Cp. Then if we know velocity triangle and then we know psi sigma, then we can find out what is the temperature rise in a stage in actual case. But now we are interested in finding out what is the pressure ratio, pressure risen in the case of centrifugal compressor from the velocity triangle. So for that we know stage efficiency of the compressor is T03 dash minus T01 divided by T03 minus T01. Actually what we mean for stage efficiency is W stage ideal divided by W stage actual. So for W stage ideal, we are having Cp into delta T0, which is ideal, and divided by Cp into delta T0, which is actual. Cp has got cancelled, so we have this as the formula for stage efficiency. When we were considering earlier thermodynamic cycle, we were not considering total temperatures, we were considering static temperatures. However, this is an improvised formula where we are considering kinetic energies also. So T03 dash minus T01 is equal to stage efficiency into T03 minus T01. So T03 dash minus T01 is equal to stage efficiency into delta T0 stage in actual case. So we will take T01 as out common, so we will have T01, we would have T03 dash upon T01 minus 1 is equal to stage efficiency, and we know that delta T0 stage is equal to psi sigma U2 square upon Cp, and then we have T03 dash upon T01 is equal to 1 plus stage efficiency upon T01, stage efficiency upon T01 into Cp divided by into sigma psi sigma U2 square. This is isentropic temperature rise in a stage, and for isentropic temperature rise we have a formula where T03 dash upon T01 is equal to P03 dash upon P01 bracket raised to gamma minus 1 upon gamma, which is the pressure rise in a stage. So we have 1 plus we have T naught 3 dash upon T naught 1, 1 plus stage efficiency divided by T naught 1 into Cp into psi sigma U2 square, and then this is equal to P naught 3 upon P naught 1 bracket raised to gamma minus 1 upon gamma, and then this is the stage pressure ratio, which is Rp stage. This is what we had to be found out. So this is what we were interested in. So having known the velocity triangle, what else we can do? First, we can find out the work required for the given compression, okay, from the velocity triangle. From the known velocities we can find out what is the work input to the compressor. Then we can find out the temperature rise in the stage. Then we can find out pressure rise in the stage. All these things we can find out for the stage. And then, having said this, we will introduce one more factor, one more coefficients for the compressors, and then for that let us write down again Ws formula what we had written down, and then for that initially without we had formula, we will go to the next slide. We had written down Ws stage is equal to U2 Cw2 minus U1 Cw1. When we say that, we will neglect the inlet swell. We said that Ws is equal to U2 Cw2, and if we go back and find out what is Cw2, if we try to find out what is Cw2, then we will go back and see what is Cw2. So what is Cw2? Cw2 is this. So if we take a typical case of backward facing vane, then Cw2 is U2 minus this. So Cw2, we will write down this velocity triangle here. So our velocity triangle was this, was U2, this was V2, this was C2, and this is CR2, okay, and this is beta 2 and this is alpha 2. So this is further, and then this is Cw2. So for us Cw2 is equal to, from this velocity triangle, it is U2 minus this distance, which is CR2 cot beta 2, CR2 cot beta 2, which is otherwise CR2 cos alpha 2, otherwise CR2, which is otherwise C, which is basically C2 cos alpha 2, or otherwise U2 minus CR2 cot beta 2. Then we will use this formula. Ws, which is a stage work, is U2 into U2 minus CR2 cot beta 2. Okay. Now we can take U2 common, W stage. This formula, whatever we are writing, here we are not considering any slip factor. Here we are also not considering any power input factor. So U2 into U2 into 1 minus CR2 upon U2 into cot beta 2. So stage work is equal to U2 square 1 minus phi 2 cot beta 2. Here we have introduced a new term which is phi, and it is called as flow coefficient. So phi 2 is the flow coefficient at the impeller tip or at the impeller exit, and then phi has a definition which is CR divided by U. So phi 2 for us is CR2 upon U2. So this is flow coefficient. Now there is one more such coefficient, and which is called as blade loading coefficient. or it is also called as pressure coefficient for the compressor, centrifugal compressor. And this pressure loading coefficient has a definition which says that it is a ratio of stage work divided by U2 square, and this is named as psi p, pressure coefficient, which is stage work divided by U2 square. We know that stage work is Cw to U2, which is rather U2 Cw2 divided by U2 square, so it is Cw2 upon U2. So this is our formula for psi p, which is pressure coefficient. So knowing this formula, we can write down the expression for Cw2 upon U2, rather Cw2 upon U2 can also be written as 1 minus, we can see over here, Cw2 U2 is equal to 1 minus, in this case if we write down this expression, then we have Ws is equal to U2 square 1 minus phi cot beta 2, then we have Ws upon U2 square is equal to 1 minus phi cot beta 2, but this is equal to psi p. So we have psi p is equal to 1 minus phi into cot beta 2. This pressure coefficient is helping us to compare the different centrifugal compressors, and we can have an analysis using this pressure coefficient. But there is an interesting curve which is a characteristic curve for the pressure coefficient with respect to flow coefficient, and then this we can see that this is a linear relation between them for a given beta 2 which is fixed, and then beta 2 is equal to 90 degree for radial, beta 2 is greater than 90 for forward, and beta 2 less than 90 for backward veins. And we can see that phi p is decreasing with respect to phi in case of backward veins, phi p is constant in case of radial veins, and phi p is increasing in case of forward veins. And then this gives us hint that this is an unstable design, and that is why this would not be preferred. But these designs corresponding to radial and for backward facing veins are stable, since phi p is decreasing with respect to phi, so these designs will be preferred. So this is how we can analyze the centrifugal compressor, and here we end the part of the centrifugal compressor, and we will see other compressor which is axial compressor in the down the line. So thank you very much for the today's class.